This talk is revolving around my graduate work, which is about approximations of Boolean functions using polynomials, and also some other combinatory statements about polynomial closure operators on the Boolean cube. So let me just begin, and this is more of an overview of some of the things that I have seen, and a little bit of my work and some related work as well. So yeah, I hope this is accessible to everyone. I'm pretty sure it will be. In fact, I think this goes both ways. I'm sure that a lot of the people will know some of the stuff that I speak today. Some people will know a lot of the stuff that I speak today. I just hope that a lot of the people don't already know a lot of the stuff that I speak. So I hope this talk is still interesting to most of you. So let's begin. So our world is the Boolean cube, right? And that's what we are interested in. And we are interested in functions from the Boolean cube to a field. And the field could be anything. In fact, we will work with fields of both 0 as well as positive characteristic. So the Boolean cube is just 0, 1 to the n as a set embedded inside the vector space f to the n for some field f. And one important parameter that we are interested in is the Hamming weight of any Boolean vector. So for any Boolean vector x, the Hamming weight is defined to be the number of coordinates, which is equal to 1, right? And pictorially, a very nice way to represent the Boolean cube is in this sense as a rhombus, where you have horizontal layers with one layer corresponding to each Hamming weight. So for instance, at the bottom, you have the all zeros vector, which is the only point with Hamming weight 0. At the top, you have the all ones vector, which is the only point with Hamming weight n. In between, you have a layer corresponding to Hamming weight n by 2, provided n is even. If n is odd, you will have two middle layers, floor and ceiling n by 2, and so on. So this is a standard way of visualizing the hypercube, and it helps in many situations. So yeah, that's about the Boolean cube that I wanted to mention at the outset. So let's go on to the kind of problems that we're interested in. So we are basically interested in representing Boolean functions using polynomials. And a very natural way to do this is, first of all, think of the function as being a function over a field. And then simply by interpolation, you get what is called an exact representation, right? A polynomial over the chosen field, which agrees with the function value at every input, right? And associated to this polynomial is the notion of the degree. And mind you, since we are working over the polynomial ring, there is no unique choice. There are several choices for the polynomial. And the least degree among those choices is defined to be the degree of the function itself. Right? Now, how do you get a canonical representative polynomial which agrees with this degree? Well, you can always restrict yourself to linear combinations of square-free monomials, because since we are concerned with functions over the hypercube, for any bit xi squared is equal to xi, because the bit xi takes values just 0 and 1. So you can always reduce the monomials modulo this relation in any representation that you start out with, and end with a canonical expression, which is a combination of just square-free monomials. And the degree of this linear combination will be equal to the designated degree of the function, the least possible degree. All right, so that's a very simple, straightforward way to represent Boolean functions using polynomials. Let's look at some quick examples, and these are sort of important examples. They'll pop up again and again during the course of this talk. So let's start with the majority function. So majority, as the name denotes, for any Boolean input, the output is 1 if the Hamming weight is at least n by 2. Right? So you have n length Boolean inputs. If at least half the number of bits are set to 1, then the output is 1. Otherwise, the output is 0. So for instance, over the reals, for majority over 3 inputs, this is the exact representation: x1, x2 plus x2, x3 plus x1, x3 minus 2 x1, x2, x3. And yeah, note that the representations could change when you change the field, right? And the degree of this is 3, obviously. And in general, when you consider n bits, the degree is going to be n. It's just that the representation is a little more messy to write down. Okay. Another popular function when it comes to studying the complexity of Boolean functions is the OR function. So the OR function in n inputs gives the output 1 if at least one bit is 1, and 0 when all the bits are set to 0, right? And in this case, we have a very neat polynomial representation, very neat exact representation, which is simply 1 minus product 1 minus xi. And this is true over any field. In fact, there is no, this is the least degree polynomial representation over every possible field. And the degree is obviously n. All right, so moving on to probabilistically approximating Boolean functions using polynomials. So how do we do that? So when we consider probabilistic approximations, we are trying to approximate Boolean functions using random polynomials. So the randomness is in the choice of the polynomial. And obviously there will be an error tolerance parameter involved, right? So a random polynomial is simply a finitely supported probability distribution of polynomials, right? It's a set of polynomials which I denote in this case as q1 to qk, and p1 to pk are probability masses assigned to each of those polynomials, and they will all add up to 1, right? So that's a random polynomial. And for any such random polynomial, we can define its degree to be the maximum possible, or rather the maximum degree among all the polynomials in its support, right? A fairly natural definition. And how do we use this to approximate functions? So for an error parameter epsilon, an epsilon error probabilistic polynomial for a Boolean function f is some random polynomial q such that the probability of agreement with the function value is at least 1 minus epsilon. It's high for every input. Okay, so once again, here the randomness is not in the choice of the input. It is in the choice of the polynomial. You take a probability distribution of polynomials. This distribution is an epsilon error probabilistic polynomial for the function f if at every input x, the randomly chosen polynomial agrees with the function with high probability. That is 1 minus epsilon. Okay.
What's the degree in, like, is there any restriction on the degree of q here?
Nothing yet, nothing yet. Yeah. So any random polynomial that will allow this condition is a legitimate probabilistic representation. Just like we had an exact representation, which need not be unique, but then we can cut down on the monomials and then reach a canonical least degree representative. Similarly, here we will sort of come down to a least degree probabilistic representation.
Yeah, okay, thanks.
Yeah, sure. So for this error epsilon, now we define the p degree. P degree is short for probabilistic degree. So the p degree of f for error epsilon is defined to be the minimum possible degree among all random polynomials which approximate f up to error epsilon in this sense, right? So the minimum possible probabilistic degree of any probabilistic polynomial for the function f when the error is epsilon. That is defined to be the epsilon error p degree of f. Okay, and the whole essentially the whole talk, the remainder of this talk is about understanding the p degree as a complexity measure. So when you talk about exact representations for Boolean functions, the degree is a very natural complexity measure. Similarly, when you talk about probabilistic representations of Boolean functions using polynomials, the probabilistic degree becomes a very natural complexity measure. And we want to understand this in different settings for different classes of Boolean functions. All right. So yeah, that's the overall theme for this talk. Right. So once again, let's look at a few examples. Going back to a majority function, outputs 1 when the Hamming weight is at least n by 2 and 0 otherwise. The exact polynomial has degree 3 in case of 3 inputs. But for majority over 3 inputs, if you fix the error parameter to be 1 by 3, then the probabilistic degree is just 1, the smallest possible degree, which is 1. Why is that? It's fairly easy to check that if you simply take a single random bit uniformly and independently among x1, x2, and x3, that will be a probabilistic polynomial for majority with error 1 by 3. All right, so the p degree has come down to 1 in this case. And more generally, in fact, the p degree could be significantly smaller than the exact degree. So, for instance, for the majority itself, if you combine the results of Smolensky from the 90s and a recent result by Allman and Williams, you can show that over any field and any error epsilon, the epsilon error p degree of majority is roughly square root n log 1 over epsilon. So for instance, if you are interested in the constant error regime, if I fix the error epsilon to be just 1 by 10, then the probabilistic degree is just square root n. That's it. But the degree, exact degree is actually n. So it's a significant saving in the complexity. And this is true over every field. So here the lower bound was given by Smolensky and the upper bound comes from a result of Allman-Williams. Smolensky's result was specific to majority. Allman-Williams' result is not specific to majority. In fact, the upper bound of square root n log 1 over epsilon works for a large class of symmetric functions. Large class of Boolean functions. It's in fact true for all symmetric functions. We'll get to that in some time. All right. So another example that we saw a little while ago, the OR function. For the OR function, the exact degree is n, but the p degree is a mystery even now. So what do we know? So over fields of positive characteristic, we know that the answer is exactly log 1 over epsilon for OR. In particular, for constant error, the probabilistic degree is a constant. Okay. But over the reals, yeah, so this result was by Rasborov and Smolensky. But over the reals, the answer is a mystery. So what do we know currently? As of now, we know that for constant error, let's fix it to be 1 by 10. The p degree has an upper bound of log n. And this is due to two independent works by Pagel, Reingold, Spielmann, as well as Tarui. And on the lower side, we have a bound of roughly square root log n, which is very recent due to Harsha and Srinivasan. And we don't know, this is the best we know. We don't know what exactly the answer is. The conjecture is that the p degree is in fact close to log n and not close to square root log n. But we don't have any progress beyond what you see here as far as this question is concerned. All right. So yeah, that was some examples. So let me go to the next. All right. So before I get here, any questions up to this point? All right. So let me continue. So I've just introduced exact polynomial representations, probabilistic polynomial representations. The second object that I wanted to talk about, which was hinted in the title of this talk, was closure operators over the Boolean cube. So let me now pause this bit here and move on to closure operators for a while. So what we are really interested in is what is formally called the finite degree Zariski closure. It's a very classical algebraic object, has been studied in several contexts, combinatorial, algebraic, and it seems to have found lots of applications in complexity theory as well. So let me just take you through some basic stuff about Zariski closures. I'll refer to them simply as Z closures for the rest of the talk. Okay, so let's stick to the hypercube. So let's take a finite subset of the Boolean cube 0, 1 to the n, and this is, as I mentioned earlier, sitting inside a vector space over a field F. For a degree parameter D, the degree D Z closure of A is defined to be the common zero set of all polynomials of degree at most D that vanish on the whole of A. Okay, so once again, this is the set of all Boolean vectors which satisfy the following property. Given any polynomial of degree at most D that vanishes at every point in A, the polynomial must also vanish at the point X. Okay, so this is the common zero set of all polynomials with degree at most D that vanish at every point in A. Okay, so it's a fairly natural object to consider, at least from the algebraic point of view, because this is a closure operator and it finds many applications in theory of ideals and the duality between ideals and point sets and things like that. Okay, so
I'm just confused with the definition. The F is not fixed. You just go through all the degree F polynomials. F,
right. So we go through all polynomials of degree at most D that vanish on A. Right. So for any F, if the left-hand side is true, then it should imply that the polynomial should vanish at X. So formally, what we are doing is we are considering the vector space of polynomials with degree at most D, which vanish at every point in A. And we are taking the common zero set of that vector space.
Yeah.
Okay. Yeah. So yeah, that's it. So quickly, a couple of very interesting examples. So let's take the point set to be the set of all points with Hamming weight at most D. So this is a Hamming ball of radius D, right? And for this parameter D, if the radius is D, then the degree D set closure is going to be the full Boolean cube. So, and if you observe this, this is a, in some sense, this is a higher dimensional analog of the simple fact, the simple univariate fact that a univariate polynomial of degree at most D that vanishes at D plus 1 distinct points must be the zero polynomial. That is what this is in the higher dimensional setting. So having weights at most D, how many weights do you have? The choices is D plus 1. Number of choices is D plus 1. The Hamming weights can range from 0 to D. If you have a polynomial of degree at most D that vanishes at every point with Hamming weight at most D, so from 0 to D, from 0 to D, so the Hamming weight has D plus 1 choices, then the polynomial must vanish everywhere. It is the zero polynomial. Okay, so that's the first example. Second is a slight variant of the first one. So take all points with Hamming weight at most D minus 1 and all points with Hamming weight at least n minus D plus 1. So it's like a set of D weights, initial D weights, and the complementary set of final D weights in the Boolean cube. And D is chosen to be at most n by 2 so that this definition makes sense. So if you choose this as your set of points, then the degree D closure is itself. No other point will be in the closure. Why is that? Because for instance, you can consider a polynomial of this kind. Take product of D many factors where each factor is a difference of two variables and the set of variables is disjoint. Okay, so there are D factors here. So this is a degree D polynomial. If you take the input with weight at most D minus 1, you will note that at least one of these factors must have both variables set to 0. And therefore, this polynomial will vanish. If you take an input with weight at least n minus D plus 1, greater than or equal to n minus D plus 1, then the complementary statement is true. At least one of these factors will have both variables set to 1. and then once again this polynomial will vanish. So this polynomial vanishes at every point in the set A. And for any point outside, for instance, you can set the odd numbered variables x1 to x2d plus 1 to 1, and the even numbered variables x2 to x2d to 0, and then adjust the remaining weights to make sure that you get the correct weight that you want. And that point is not going to be in the closure because the evaluation of this polynomial at that point is 1. And for every other point in that same layer of the same weight, you can consider an appropriate permutation of these coordinates and get a suitable witness polynomial. So moral of the story is no other point outside the set A will be in the closure. For each such point, you can permute the coordinates of this polynomial suitably and obtain a witness polynomial. Okay, a witness polynomial is a polynomial that vanishes on the given set A but does not vanish on the chosen point. It shows that the point is not in the closure. All right. So yeah, that's as far as, so these are the two most interesting examples, even in the context of this talk. So that's it. Okay, so in fact, the statement about Z closures is more popular. When I say popular, what I mean is more applicable, actually. So it's more applicable in the contrapositive sense. So what is the contrapositive of determining a degree dz closure? So it means this. Suppose you have a set A and you also know what the closure is. Okay. And now you have a point that is definitely known to be not in the closure. So you have a point X that's not in the degree D closure of A. But you have also a polynomial P which vanishes on the set A but does not vanish at the point X. Then you can say that the degree of P is greater than D. It has to be at least D plus 1 because the definition of the closure says that if the degree is at most D, then it should have vanished at the point X as well. Right? So that's not true, and therefore the degree of P is at least D plus 1. And we use this in the sense of saying if a polynomial vanishes on a set but does not vanish on some other points outside, then the degree of that polynomial is large. That's the kind of statement that we want to make. That's the kind of statement that finds applications in, for instance, probabilistic approximations as well as some other places in complexity. Okay. So yeah, so I'll come back to this contrapositive once again in more detail. So let's look at a concrete instance of all of these things coming together. Okay, all of these things coming in action. So yeah, once again, good time to pause. Is there anything that's not clear up to this point? I can elaborate. Any questions? All right, so whatever we have seen so far, let's see all of it in action in a very simple argument for the lower bound of majority, the p-degree lower bound for majority. So this is a proof, it's basically an argument of Smolinski, but you will also find the same idea in the work of Rasborough. So it's usually attributed to both of these people. And it's a very simple proof. It's possible that some of you have seen this in some complexity theory course, because this proof usually finds itself in a complexity theory course itself. It's a very simple proof. But I am mentioning this here in all detail because first of all, it's a very short proof. And secondly, even today, for if you look at any proof of a p-degree lower bound for a Boolean function, it's highly likely that somewhere within the details, you have an argument that looks very much like this one. So most p-degree lower bound arguments results that we know even today fall under the shadow of this basic proof technique, which is why I want to just illustrate this in a little bit of detail. Okay, so yeah, so what's the statement? So we need two basic facts, first of all, about the hypercube and the polynomials. So one is called Yao's min-max principle, and I'm not mentioning it in full detail. I'm mentioning it in the setting that we require. Okay, so for a Boolean function f and an error parameter epsilon, the following two statements are equivalent. One is that you have a random polynomial, which is an epsilon error probabilistic polynomial with degree at most d. Okay, so there exists a probabilistic polynomial for error epsilon with degree at most d. This is equivalent to the other statement, which is that given any probability distribution on the point set, on the hypercube, on the Boolean cube, there is a explicit polynomial q with degree at most d that agrees with the function f with high probability, where the randomness is in the choice of the input now, not in the choice of the polynomial, right? So on one hand, you're saying that here is a collection of polynomials which agrees with the function with high probability at every input. That is equivalent to the statement that for any probability distribution on the inputs, you can choose a polynomial with the same degree bound that agrees with most points, agrees with the function at most points, in the sense of the randomness coming from the choice of the input. Okay, so these are equivalent statements, and it's really important because once again most p-degree lower bound proofs start with the statement let q be an epsilon error probabilistic polynomial, and then by Yao's min-max, for a certain distribution we get a certain polynomial, and then you work with that polynomial. That's more or less a basic template for all these proofs. Okay. All right, the second fact is more about the distribution of points in the Boolean cube, which is that for any constant c, there is another constant case, is that if you look at n by 2 plus minus c times square root n Hamming weights, then that contains at least, sorry, k times square root n Hamming weight, that contains at least c times 2 to the n points. So yeah, sorry, there should be a k here. Sorry, there should be a k here. It's a small mistake on my part. Yeah. Sorry. So yeah, the idea is a constant deviation of, a deviation of constant times square root n from the middle layer. Okay, if you just start from the layer n by 2 and go constant times square root n both sides and take all the points in the hypercube with Hamming weight in that band, that will contain a constant fraction of all the points in the Boolean cube. Okay, that's the basic statement, and that's what we will use in some of the arguments that we want. Okay, what exactly these constants are not really so important for us. So yeah, I hope this mistake is not going to be much of a problem. So, yeah. So what is this proof? So recall the majority function gives the output 1 when the Hamming weight is at least n by 2. So suppose the p-degree of majority is d for error epsilon. Okay. So by Yao's min-max, there is a polynomial q. This is not a random polynomial. This is an explicit polynomial q with degree at most d, such that it agrees with the majority function on most points. In other words, the error set, I'm calling it E here, has size, or rather has fraction at most epsilon, right? So the error set has size at most epsilon times 2 to the n. What have I really done here? I have chosen the uniform distribution, and Yao's min-max for the uniform distribution translates to exactly this statement. Okay. So the polynomial q has the correct degree bound and it agrees with majority on most points. All right. Now let's go to fact 2. Okay. So what does that say? From the middle layer, if you simply go constant times square root n many layers forward and backward, you would have covered a constant fraction of all points in the Boolean cube, right? But epsilon is supposed to be a small number, a sub-constant ideally. So epsilon times 2 to the n is a very small number. It's not a constant fraction of the number of points in the hypercube, right? So you can actually consider n by 2 minus square root n as your degree parameter, a new degree parameter, capital D. And this will already exceed the number epsilon times 2 to the n, because the number of monomials of degree at most D is going to be close to a constant fraction of the number of points in the hypercube, but epsilon times 2 to the n is much smaller than that. Okay, so you can adjust the constant inside this theta and make sure that such a D can be chosen. That's not an issue at all. All right, so what do we do with this parameter? So since this number is much larger, and the number of monomials is much larger, you can just set up a linear system and get a non-zero polynomial P, which vanishes on this error set. Okay, the set of points at which we have disagreement. It vanishes on this error set and its degree is at most capital D. All right. And now we simply multiply. So a simple check of the vanishing properties of P as well as Q will tell you that the product P times Q, which I call here R, will vanish at every point with Hamming weight at most n by 2 minus 1. Okay, it will vanish at every point with Hamming weight less than n by 2. However, it's non-vanishing as a function on the upper half. So there is at least one point with Hamming weight at least n by 2, such that R is non-vanishing at that point. Okay, this is very easy to check just by looking at vanishing and non-vanishing properties of P and Q. Okay, so what does this say? Now comes the popular contrapositive way of looking at closures. So the closure statement here is the following. If you look at the Hamming ball of radius n by 2 minus 1, then the degree n by 2 minus 1 closure is full. Right? But now here's a point with at which the polynomial is non-vanishing, but the polynomial is known to be vanishing on the Hamming ball of radius n by 2 minus 1. Therefore, the degree of R should be at least n by 2. Right? So this is exactly the contrapositive form of the closure statement that I was mentioning. Okay. Right. So the degree of R is at least n by 2, but now if you look at it, the degree of R is the degree of P plus the degree of Q, right? So little d plus n by 2 minus theta square root n log 1 over epsilon should be at least n by 2, and therefore d is at least square root n log 1 over epsilon. Okay, so that's the proof for the lower bound, right? So yeah, anything that's not clear in this proof, this is the only proof in this talk, and it's also a central idea. So yeah, let's get it cleared if something is not clear. All right, so yeah, that's what it is. And right, so this turns out to be, as I said, a fairly central idea in the whole of this line of inquiry. So when you want to talk about 3-degree lower bounds for certain functions, one very important way of approaching the problem is to apply Yau's min-max and then choose an appropriate distribution with respect to which you will get such a polynomial Q, and then you can sort of go ahead and get some, again, an appropriate closure statement which will finally give you the lower bound, right? So there are two questions here. One is you need the correct distribution, and then you need the correct closure statement, right? And both of these are fairly difficult problems in general. Okay, so yeah, so some other instances of a similar argument working for other functions. What is the difference? The difference is, as I said, it's a difference in either the distribution of points that you choose or in the closure statement that you employ, or both. Okay, but the basic outline is the same, modulo a few uh, technical lemmas, so to speak. So what are some other lower bounds that we know of this kind? So let's fix a base b, at least 2, and then the function mod b comma I in bits is defined to be, the output is 1 when the Hamming weight is I modulo b, and 0 when the Hamming weight is not I modulo b, right? And Smolensky's proof technique can actually be used to give pdeg lower bound even for this function. So over fp fields with positive characteristic p, if b is at most n by 4 and b is co-prime to the choice of p, then the epsilon p degree is at least square root n log 1 over b epsilon. Now that's a small technical thing that comes in between, but if you choose a constant base, then it's the same as the majority lower bound of square root n log 1 over epsilon. Okay, and similarly for the OR function, again in positive characteristic, the lower bound is p times log 1 over epsilon. When you consider p as a varying parameter, if p is constant, it is just log 1 over epsilon, as I mentioned in a previous slide. Okay. Over the reals, however, as I said, it's not clear. We don't know exactly what the p degree is. The best we know in full glory is this. We know that it is at least square root log n by log n squared plus log 1 over epsilon. Okay. And for constant error, if you're ready to ignore the smaller polylog factors, then it is essentially square root log n. And on the upper side, we have log n, and we don't know where exactly the answer is. So these are some lower bound statements which follow from a similar proof technique. Let me also talk a bit about an upper bound proof. Okay. So this is where the Allman-Williams result comes. So a Boolean function f is said to be symmetric if the definition is quite clear from just the terminology. The value depends only on the Hamming weight of the input. So for any x and y with the same Hamming weight, the output is the same, right? And Allman and Williams actually give a probabilistic polynomial construction for any symmetric function f, and the degree bound is square root n log 1 over epsilon on the upper side. Okay, because this is an explicit construction of a probabilistic polynomial. Right. So let's look at it in slightly more detail. So the basic idea of Allman-Williams is the following. So if you look at symmetric functions, it can be written, any symmetric function can be written down as a combination of simpler functions, which in this case are threshold functions. So what's a threshold function? So fix a parameter t as a threshold parameter. And the t threshold is the function which gives you output 1 when the Hamming weight is at least t, and 0 when the Hamming weight is less than t, right? So in particular, the functions that we have seen so far, majority is the n by 2 threshold. The OR function is the 1 threshold. Okay. So more generally, what Allman and Williams show as part of their main work is that when you take the threshold parameter t, its p degrees at most square root n log 1 over epsilon. Okay, this is the basic statement. And then you can use this fact that every symmetric function is a linear combination of appropriate thresholds with some more finer arguments. You can make sure that this bound works for every symmetric function. Okay, but the very basic statement that lies at the heart of the proof is this: for a threshold function with parameter t, the probabilistic degree is at most square root n log 1 over epsilon. All right. So why is this interesting? So in our work, so this was joint work with Srikanth Srinivasan and Utkarsh Tripathi, we could improve this a bit. So now for threshold parameter t, the probabilistic degree is actually, it can be shown to be square root t log 1 over epsilon plus log 1 over epsilon. So the additive factor is not so important. It just pops up as part of our analysis. The main savings, however, is in the square root t factor. Right? So from square root n, the p degree, we can show that it has come down to square root t. And we don't really give a better construction as such. The probabilistic polynomial construction is the same as Allman and Williams. We could just observe that the analysis can be tightened to get this p degree bound. Okay, and we go ahead with this and sort of characterize the probabilistic degree of all symmetric functions up to a polylog factor loss. Yeah, so that is for another day. I'm not getting into the details of that result. So yeah, so this was about p degree upper bounds that I wanted to present. Let's go back to the Z closures. Okay, there's another kind of statement that I wanted to present today. So this is a lemma by Hegedus from 2008, if I'm not wrong. So let's fix a field FP. 2009. So Hegedus showed that if you consider any Hamming weight k between p and n minus p, okay, and if capital P is a polynomial which vanishes at every input with Hamming weight k, but does not vanish completely on the layer k plus p. If there is an input with weight k plus p at which the polynomial does not vanish, then the degree is at least p. So as you're familiar with, by now, this is a closure statement, right? What it says is that the layer k plus p is in fact in the degree p minus 1 closure of the layer k. All right, and this is interesting to us in a slightly different way. So Srikanth very recently gave a robust version of this statement. And how does that look like? So note that in the Hegedus version of the statement, we have complete vanishing on a given layer of weight k and just non-vanishing at a single point. There is no more guarantee. The guarantee of non-vanishing is at a single point at the layer k plus p, right? But in a robust version, you relax things a bit. So instead of complete vanishing at the layer k, you can say that the polynomial is vanishing at most points of the layer k. And instead of the single non-vanishing guarantee at the layer k plus p, you can say that it vanishes on a tiny fraction of points at the layer k plus p. It's not a single point, but a little bit more than that. Okay, so the exact parameters turn out to be this. So I'm not even reading them out, but it's essentially saying that if there is a if k is a weight between 100 times p and n minus 100 times p, again the constant 100 can be changed. It's not so important. So for this choice of k, if capital P is a polynomial such that it vanishes on most points of the layer k and does not vanish on a tiny fraction of points on the layer k plus p, then the degree of the polynomial is at least omega p. Okay, so we don't have a degree bound of exactly p, but we have degree bound of omega p. Yeah, I just noticed there's also a small error here in the second part. This is n choose k plus p because we're talking about the fraction in the k plus p at layer. Yeah. Okay, so yeah, that is a robust version of this statement. And why is this interesting? So let's go to an application of this. So if you look at a variant of the threshold function for the middle layer, so you have the majority which gives you output 1 for Hamming weights greater than or equal to n by 2. Consider the variant which gives you output 1 when the Hamming weight is exactly equal to n by 2 and 0 everywhere else. Okay, so that's the exact mid threshold, I've called it, or also called exact majority. So using this robust version of Hegedus and following a similar outline as Smolensky's proof, you just have to choose the probability distribution a bit more carefully and then follow the same proof outline as Smolensky. You can show that for constant error 1 by 10, this does not work as well for variable error epsilon, but for constant error 1 by 10, the p degree is in fact square root n. Okay? There's a theta here, sorry. So it's theta square root n. Okay. The upper bound of square root n already comes from Allman-Williams. We show that it is actually tight. Okay. So that's a clean application of not exactly Hegedus, but a robust version of Hegedus. Right. So, all right. So before going on to open questions, are there any questions up to this point? So this is formally the end of the talk. It's only some open questions that I wanted to mention. All right. So where are we up to this point, and where do we go ahead? So a few open questions. So what we do know, we know a bit more than the standard Hegedus lemma as of now. So in a joint work with Srikanth, what we know now is that over fields of positive characteristic P, for any degree D, okay, now the degree parameter is not P minus 1 or P. For any degree D, if you take a layer K between D and n minus D, then the degree D closure of K, of the layer K, is in fact the set of all layers with Hamming weight equal to K mod P to the L, where L is this number log D plus 1 to the base P, but nothing complicated about it. L is simply the number of digits required to represent D in base P. That is what L is. Okay. So L is a number of digits that are relevant for the PLE representation of D. And what we say is, when K is between D to n minus D, the Z closure of the K layer is a set of all layers with Hamming weight equal to K mod P to the N. Okay, so it's like the set of all cyclic shifts mod P to the N of the layer K. Right. So it's a stronger statement than Hegedus. In fact, it encompasses not just Hegedus, but a few more variants of this that you find elsewhere in the literature. And it's a more general statement. So what does this give? I mean, we have already seen that Hegedus seems to have some applications for a p degree lower bounds. So are there p degree lower bounds applications for this result or some variant of this result? Right? So more general closure statements, do they give us p degree lower bounds? That's a fairly open question. It's not a very concrete question, but it's more of a line of thinking. General closure statements, do they give us p degree lower bounds? Okay. So in relation to this, another variant, another direction is to consider multiplicities. So why do we simply talk about vanishing of a polynomial at a point and not go on to consider vanishing with higher multiplicities, vanishing of a polynomial as well as its derivatives up to a certain order? So in relation to that, we have this conjecture about, so we call it a multiplicity closure conjecture, but we have not really studied multiplicity closures in any detail. So this is probably the only statement, concrete statement that we have as a conjecture, which is, so over Fp, again, for any k between p to n minus p, if capital P is a polynomial that vanishes with multiplicity m, which means the polynomial vanishes and all its derivatives of order up to n minus 1 also vanish at each point with Hamming weight k on the kth layer. And if there is some point on the k plus pth layer at which p does not vanish. So the non-vanishing is simple. There is no multiplicities involved. But if there is vanishing with high multiplicity, multiplicity m at the kth layer, and simple non-vanishing at the k plus pth layer, then we think the degree of p should be at least p plus m minus 1. So if you put m equal to 1, this comes down to Hegedus. So that's a multiplicity extension of Hegedus. And then obviously, if this is true, what sort of application does this have to lower bounds? So one thing that we are really interested in knowing, and there is no lead, and I don't think there is really any concrete piece of work that involves multiplicity closure statements for p-degree lower bounds. We don't really know of any argument that employs multiplicity vanishing to say anything about probabilistic degrees so far. So that's something worth pondering about. And also this famous or very popular conjecture that has been sort of explored now and then for quite a long time. Over the reals, what is the correct answer for the probabilistic degree of OR? So it's between log n and square root log n, and we conjecture that it is close to log n, not square root log n. So yeah, these are the three open questions that are very, very close to what I just presented, and also very close to the work that I've done so far. Yeah. So yeah, that's the end of the talk, and if there are any questions, I'm happy to take them.